you let me know. You know,
We can, yeah, we can.
now it's 3. Shall we start or we wait or yeah?
I think we can start and then I'll double check it is recording the whole video.
Okay, then yeah, sure. Let's get started. So it's my pleasure to introduce Nan Jiang. He's my PhD student with me for a few years, and he works at the intersection of automatic reasoning and learning. And today he's going to give us a talk. His PhD defense. It's going to be integrating automatic reasoning with machine learning for structured prediction and scientific discovery. So yeah, the stage is yours, and let's welcome Matt.
Thank you for attending my thesis defense, and also thank you for all the committee members to attending my talk. Today, I'm going to introducing my research, which is integrating automated reasoning with machine learning for structural prediction and scientific discovery.
I think that's with your clicker. Uh-oh.
Okay, now it works.
Okay.
So
William, just check. You can still hear us, right?
Yeah, looks good.
Okay. Machine learning and automated reasoning are two foundational pillars in artificial intelligence. Machine learning.
So this comes again.
On the one hand, is a bottom-up and inductive system. It can fit the data distribution pretty well. In this community, early example, including perceptron algorithm, to last 20 decades, support vector machine are quite popular model. Recently, generative model are quite popular. Automated reasoning, on the other hand, is another community, is a top-down and deductive system. It builds a precise model from the problem description. In this community, successful example including satisfiability solver, satisfiability modulo series solver, and also mixed integer programming solver. So the two machine learning and automated reasoning has its advantage and also has its own limitation. Machine learning, on the one hand, is challenging in providing formal guarantee. It has hallucination problem where the generated output are sometimes fabricated and even false. In the rare and unseen cases where you don't have those training example, it may violate critical constraint. Automated reasoning, on the other hand, builds a region model. You need to know, and also make agreement for the problem formulation before you write the software. And it's difficult to adapt to evolving data distribution, and also it's quite non-trivial to understand complex data like text and images. Here's one example for machine learning. Here's I play with ChatGPT, which is the latest machine learning model about a logical reasoning problem. The problem I asked about ChatGPT is Mike's mom had 4 kids. 3 of them are Luke, Louis, Drake, and Matilda. What's the name of the 4th kid? This problem requires large language model to understand the language and also to do logical reasoning. And then currently the ChatGPT cannot give you a direct answer. I try again, it still cannot do it. As the audience has an answer. So for those of you may already seen this example, don't tell the answer. Can you try and give it? Okay, great. So thank you for answering my question. So as a human being, we understand the context and then do logical reasoning in our mind. So currently ChatGPT cannot do it. And then one of the famous figure in this community, Yang LeCun, commented This large language model is still at cat level intelligence. It is non-trivial to do logical reasoning, and then has other capability like persistent memory. On the other hand, automated reasoning has its own intrinsic difficulty. Here's one of the typical example you play with those satisfiability solver, which is an example in automated reasoning. You give in several variable and then connected by several logical operator. So satisfiability solver will give you a feasible assignment very efficiently. However, to relate the data distribution with each variable is non-trivial. And also to relate those complex input data like millions of words or millions of pixels to those variables also become hard to process. So here's just a brief summary, which we just talked about. Machine learning has its pros and cons, and automated reasoning has its own pros and cons. The two topics, a class of problems in structure prediction and scientific discovery I studied, are still beyond the reach of machine learning and automated reasoning when they are applied in isolation. So my general idea to tackle this problem is to integrate machine learning and automated reasoning by taking the benefits of two systems. So my key strategy to embed diverse reasoning solver as differentiable modules into a neural network. After doing the integration, you will have two benefits. The first benefit is you got formal guarantee of constraint satisfaction. The second benefit is after the integrated system allows you to learn on higher dimensional data with better accuracy, which you have the scalability. So for the rest of my talk will be partitioned into three parts. The first part is on formal guarantee, and then the second part is on scalability, and then we will briefly take a look at what the future will be like. So now I'm going to talk about the first part, which is integrating reasoning with learning to ensure constraint fraction for structure prediction. So here is one of the example in structure prediction. The task is called delivery route planning. And the task asks you to recommend, given a set of location, you need to recommend a route so that you need to satisfy the delivery request. Basically, you need to suggest a sequence of location, visit each location once and only once. And also you wanted to meet the driver's implicit preference. The driver's implicit preference is reflected in his historical data. For example, this is the historical data where the driver previously pick a route for this relocation from school to park to market. And the driver has its own preference from among all the feasible routes, he will pick one of them. And this is reflected, this kind of travel record reflects its implicit preference. Typically, machine learning model like transformer is good at learning those preferences from the historical data. However, it become quite difficult to ask those machine learning models to always generate a feasible route. Reasoning solver explicitly in this context, traveling salesman problem solver can give you a feasible route. However, the route you typically get is a route of shortest distance or shortest travel time. And then these are different from the implicit preference from the historical data. In our formulation of an integrated system, we can using neural network to learn the driver's implicit preference. And then we can using the reasoning solver to satisfy the delivery request. Not only in the route planning example, also we find the code generation example share the same problem. So here, the task is called code generation from natural language. The task is to predict a SQL program so that the program reflects the user's query describing natural language. And also the program is at least executable. Here is a problem. The problem is you are giving a SQL table, and then the user wanted to get access to the SQL table by asking in natural language, how many schools did the player number 3 play at? And then we want a system that can output a SQL query, which is select count school where number 3 equal to 3. So right now, machine learning methodology like transformer applied to solve this problem, which is very good at understanding those queries described in natural language. However, it is still difficult for those models to always generate an executable SQL query. And reasoning solver in this domain, including SQL grammar engine, it will give you some kind of existing SQL query template. However, this SQL query template may be very different from the user's intention. And the main limitation is this SQL grammar engine cannot understand those natural language. So in our integrated system, we can have a neural network module that understands the meaning of the intention described in natural language. And then we can ask a reasoning solver to satisfy the SQL grammar. So the main design principle of the two problems that I just mentioned can be designed in this way. We can have a machine learning model in this context. It's typically a recurrent neural network to learn the representation from data. And then we wanted to using a automated reasoning solver to satisfy different type of constraint. Specifically, we are using a decision diagram to filter out those infeasible output. After that, we will draw a sample, a feasible sample from the model. So to make the whole system become differentiable, which means that we have a loss function. The loss function is to we wanted to compute the gradient of the loss function to adjust the parameter inside our neural network. So there are some extra steps are involved. So we call the system we designed on the right is constrained reasoning embedded structure prediction, which is called COSET for short. Here is a basic background story on what is a decision diagram. Decision diagram basically is heavily used in combinatorial optimization or operation research. It represents the set of feasible solutions into a space compact directed acyclic graph. So take this graph as an example. It is defined for three variables, y1, y2, y3, which can take three different values, v1, v2, v3. And then each pass from the top layer to the bottom layer represent a variable assignment for three variables. Here is one of them. So for this blue pass, this means y1 for the first layer output, y1 equal to v2, second layer output, y2 equal to v3, last layer output, y3 equal to v1. The compilation basically means that given a set of constraints, we wanted to delete those passes that violate those constraints. So in the history, the graph based on how you delete those passes or the space to store those graphs may be taking a lot of memory. So there are some extra heuristics to merge those passes to reduce the memory consumption. So how do we the graph we have here does not naturally exist. We need some extra steps to construct those graphs. Here's just one of the analogy on how to obtain those graphs. So we may start from one of the graph and knowing the constraint that we want the variable to take different assignment. Meaning, in this example, that those assignments that those situations where v2 equals to y1 equal to v2 and then y2 equal to v2 should not be considered. So we are going to delete those extra outgoing edges where y2 has the same assignment with v2. Similarly, when y1 equal to v3, we are going to delete y2 equal to v3. This kind of strategy that start from a small decision diagram to a relatively larger decision diagram by filtering out those violating passes will ensure the final obtained graph satisfy all the constraints. Let me know if you have any confusion so far.
I have a question. So how can you use this decision diagram to model to actually model your problem that you talked about in the beginning? The delivery route problem and the language generation problem. How can you use this decision diagram?
Yeah, that's a good example. So, for example, for the for the route generation problem. So this is if we take a look at this example. So this example is saying that um, we are giving three locations, and then it could be V1, V2, V3. We want to pick a route, and the route can start from V2, V3, V1, and then the route can also be starting from V3, V2, V1, or some others. So given those constraints, if we have a graph, then can maintain all the feasible passes, and then starting from the first layer, and we are going to either pick the left one or the right one. So this graph will ensure you are only picking feasible passes from the graph. All the others are not considered.
Okay, so the route needed to visit.
The route needed to visit each location once and only once.
Okay, so that's why you have, you know,
Uh,
all the location sequences that you have right now.
Yes,
They are
They
they,
take a
they have
different-
exactly one location.
one location once and only
Okay.
once.
All right. Okay. Now, how about the language generation?
The language generation. For example, for the language generation, we wanted to keep track of during each time of prediction. For example, so the grammar basically say that it should be starting from select keywords. So and then it should be so the first of the generated token should be select all the and then you only have one outgoing edges, which is the label must be select. And then the second one could be depend on how many available keywords you are allowed to take. Then you have several keywords like could be count or some other keywords. And then you have several outgoing edges specify which keyword is generated. And then depends on depends on this is the free word that you can pick any word. It could be the word from the all the words are from the input query. After that, you have to enforce that following that there should be a keyword where. And then all the other keywords should be not considered. And then this is the equality or inequality statement. Basically, we check for three steps, consecutive steps, whether the second step is a equality or inequality. And then the first and the third word can be arbitrary word. So this is you build a diagram that follows the sequence of generation.
Okay. There is a chat in Zoom.
Yes.
So is that a question?
Unfortunately, seems to be internet, so I can hear well. I will watch the recording. Yeah, basically, Professor Honorio, I can hear it. And he has some question, but he will watch the video and then ask me after that.
Okay. Yan, can you hear us? Can you participate in the discussion in the end?
Who is this question addressed to?
So one committee member, he said there is some internet issue. He is in Australia.
Sure.
And he said he can hear the defense, but he cannot see the slides. So he said he will direct the questions after he watched the video of this defense later on. But I was asking if Yan is here and if he can participate in our discussion among the committee members in the end. So is Yan here?
I need to.
Maybe he dropped out. Okay,
dropped out.
Okay. Then his discussion will be after the defense. Okay, all right. Okay, make sure that this is recorded.
Sure.
Yes,
Yeah,
this
it is recorded.
Okay, good,
Yes.
good. Okay, go ahead.
So we just talk about what the decision diagram means, and also now we wanted to combine with the neural network. So a natural analogy is an output from the sequential neural decoder correspond to a path that you see on the right. So here is an analogy. So at the first step, we have some input that the neural network encoder reasons of this input and then generate a vector. The vector will be decoded by a recurrent neural network. For the first step, the neural network is about to predict the first output, and then the decision diagram is at the first layer. So the decision diagram told us that there are only location 2 and 3 available. So location 1 is not considered, and the neural network, based on the probability score generated by the recurrent neural network, is going to sample one of them. So here, it sample y1 equal to v2 correspond to the graph that you wanted to pick the left one. Based on our prediction, the graph will move to the second layer. Now it will follow the left edge and then move to node U1. The U1 told us that their location V1 and V3. So it told us basically location 2 is not considered. You can only pick between V1 with probability 0.2 or V3 with location probability 0.5. The neural network will roll a dice and then pick one of them. So location Y2 will equal to V3. This corresponds to you pick the right edge is the graph, and then the decision diagram will move to the third layer, node 4, based on the prediction. So the third layer told us only location 1 is available, all the other is not considered. So the location 2 and 3 are deleted, only 1 is available. So the neural network will roll a dice and make a prediction. So this sequence of prediction correspond to you descending along the decision diagram, and then the neural network learns the probability score of those generated sequence. So now let's shift gear and then move to the
Now, before you talk about the experimental evaluations, so in this specific example, the starting point that we needed to, do this neural symbolic integrated approach is because, we have data-driven part that, we need to capture, some user preferences, and then we have hard constraints. Can you talk about that? Which part of this architecture that captures individual users, user preferences, and how this is being captured?
Yes. So the formulation is designed for data-driven tasks subject to those hard constraints. So the neural network, which is the encoder and the recurrent neural network, the parameter here, after rounds and rounds of gradient descent, they will capture the learning preference by saying that it has a higher likelihood of generating a output sequence that match your ground truth. If you ask it for thousands of generated sequence, then the majority of them can meet your ground truth generated sequence. And then the hard constraint here is compiled as a decision diagram, basically to enforce the generated those infeasible output are not generated from the whole system. So the generated output from the whole system is always feasible. So this helps this task to have a constraint satisfaction guarantee subject to those constraints. Okay, cool. Thank you. Thank you for the question. Now let's shift gear and then looking at the experimental evaluation. So the first experiment is on delivery route planning. The task asks you to recommend a route so that it can satisfy the delivery request. which means it visits each location once and only once. And then you want it to meet the agent's implicit preference reflected from his historical traveling data. We are comparing our method with conditional generative adversarial net at that time. So what we find is when we make the problem size larger by increasing the number of maximum location, we find the neural network model performance of generating a valid route quickly decreasing, meaning that if we ask a neural network to generate a feasible route of 10 locations, then most of the time it cannot do the job. And then we ask our call set to do the same thing. We find because we explicitly integrate those route constraints, our generated output always generate a valid route. The second evaluation is during learning, we evaluate the learning objective by saying that we find that the classic conditional game model, the objective oscillate greatly throughout the training iteration. If we integrate our constraint satisfaction layer, then we find the oscillation become less, and then we find that the model is gradually improving. So this helps the model to learn the parameter stably. Otherwise, you will never know whether your model has already learned the preferences because of high oscillation, or it completely learn nothing. And the second task is to predict a SQL program so that the program reflects the user's query described in natural language. And also we want the program to at least be executable. The first evaluation is we evaluate whether the generated SQL is valid. We evaluate on two datasets. Easy dataset, meaning there are less requirements, the SQL query is short. And then the hard dataset, meaning there are a lot of requirements, the query is long, and then the generated SQL sequence is long. So we find that when evaluated on a harder dataset, a pure neural network model tends the performance drop. On harder dataset, it has 83% of time to generate a valid SQL. Our method explicitly enforce those SQL grammar into the generation, so it always generates a satisfying, which means it's an executable SQL program. And we evaluated whether the accuracy, meaning that using the same generated SQL, query the database, whether the return item is the same. So if the return item is the same, then we consider it accurate. Otherwise, we consider it not accurate. So we find that under this evaluation, our generated SQL give you a roughly 4% improvement in terms of accuracy. So the conclusion here is by integrating those constraints, our method not only helps the constraint satisfaction and also improve the learning accuracy. We also consider some other code generation tasks. Basically, there is a task which is called web service program that you're using those natural language query to control the smart devices in our home. So we evaluated on two largest data set, IFTTT and Zapier at that time. We find using the first evaluation metric is whether the generated program can be executed between different smart devices. So neural network can generate roughly 88% of the time of an executable program. Our method by enforcing those knowledges between those smart devices and their available functionality. So the constraint is enforcing that certain smart devices has only a fixed set of function. You cannot ask the devices to do something that they cannot execute. So our method by enforcing those knowledge help you to generate always valid program. And we also compare the accuracy, meaning that whether the generated program is exactly the same as the ground truth output. We find that integrating those constraints help you in terms of improve the empirical accuracy. So we just talked about a paradigm about integrating constraint, and in the real world, there are many diverse form of constraint. For the we consider a different form of constraint, which is called logical CNF set logical constraint. The constraint can look like this format, which equals some Boolean variable and then connected by some logical operator. And then our idea is actually inspired from a recent progress on the theory. So it's called the Lovász local lemma theory. So basically, we still have the same pipeline that we wanted to using a neural network to learn the representation from the input, and then we're using a constraint, a new constraint-based sampler to give us a feasible variable assignment. So the Lovász local lemma theory has a long history. It was first of all mentioned by Erdos and Lovász by 1973. Recently, Moss and Tados gave an algorithmic version talking about how you can find such an instance that satisfies all the constraints. And in 2019, a group of researchers gave a probabilistic analysis on the algorithm they proposed. So basically, they are saying that giving a set of Boolean variable x1 until xn, each of them can either choose false for 0, 1 for true. And then you are having a set of logical constraints that represented as a conjunctive normal form. The algorithm will give you a valid sample from a product distribution subject to the constraint. So after knowing the history, we find that the execution of this algorithm can be easily transformed into matrix computation. And then we write down the exact matrix computation and embed this whole process into a neural network module, into the learning pipeline.
So an existence proof. So proof of what exists?
Oh, yes. So the earliest example is so there exists a satisfying assignment that satisfy all the constraints if the constraint itself are almost independent, meaning they are not likely to happen
for a specific kind of
constraint.
Conjunctive normal form.
Yes.
Okay. That those kind of conjunctive normal form always exist. Or with high probability, it exists a solution.
A solution.
A satisfying solution. Okay?
Yes.
And this algorithmic LLL
is saying that so after tell you there exists, and then they tell you 3 line of code how to find such a satisfying assignment.
So it's basically an algorithm that can generate a satisfying
assignment.
Okay. And then this probabilistic,
this probabilistic analysis is saying that if you follow this algorithm, then the generated sample is actually drawn from a specific distribution, which is the product distribution subject to satisfy the constraint.
Okay, so which means that all those, so you generate
when the algorithm terminates, it will give you a valid sample, satisfy all the constraints, and then the sample are drawn from a specific probability distribution. Does that okay? Let me know if you have further questions. So
can I ask one question, or maybe you're already going to answer it in the next slides? Are you going to, if you were to embed this inside the core SP framework? Will you explain that also in the slides?
I'm not. We just briefly talking about this. We didn't like show the exact steps how to do the exact embedding. So the exact embedding will we can talk about after this. So I didn't have an exact slide to show you how to do it with exactly the neural network.
Okay, we can do that then after the presentation.
So here's a analogy on how this algorithm works. So here we having 3 Boolean variable, and then we're having this constraint. So the first step is to draw from its own distribution, x1 draw from P1, x2 draw from P2, x3 draw from P3. And then after this assignment, after that, we find x1 equal to 1, x2 equal to 0, and then x3 x2 equal to 0. And we check the constraint, and we find one part, the second clause is violated. So according to the principle of this algorithm, it asks you to resample the related variable here. So because C2 is violated, we are going to resample x1 and x3 according to its own distribution. So after the resample, we find that x1 and x3 now got a new assignment. x2 will stay the same. And then we look again at the constraint. We find the first one is violated. C1 is violated. So we will only resample those variable inside C1. So after the resample that we are going to resample, so we make us a new assignment for x1 and x2. x3 will stay the same. After these steps, we check again. We find all the assignment satisfy the constraint. This is basically the procedure guided by this robust local lemma. So specifically in this context, the neural network we are mentioning here is a marker random field. The parameter inside the marker random field learns the data distribution from the input. And then the constraint reasoning sampler is inspired from this theory, and it gives you a feasible variable assignment according to this logical constraint. So the output is a feasible variable assignment for each of the variable. In the experimental evaluation, we consider whether our method is efficient. So we consider different problem sizes of those constraints. So the problem sizes go from 10 variables to 20 variables. And then we consider drawing the same amount of feasible assignment, what is the empirical running time. So we find our method compared to all the other methods, our method is currently the fastest method. So there's the other method which is shown in green here. The green sampler is called a quick sampler. However, we find that it does not give you a constraint satisfaction output, meaning that if we evaluate whether the generated output is a satisfying assignment, we find this quick sampler output when we consider more and more larger and larger problem sizes, we find it on the largest scale, it does not give you a less than 1% satisfying assignment. So by far, we can claim that our method is the fastest sampler with constraint satisfaction guarantee. So the second case is we consider other cases where could be a mixture of binary valued and real valued constraint. So this is typically designed when we are interacting with large language model, and then the constraint can be binary, like certain phrases or certain keywords must be appeared during text generation. Real valued constraint can be we want the sentiment of those sentences to be positive, or we want the sentiment of those sentences to be negative. So our methodology developed at that time was well received by this community. Actually, one of the neurologic method, which was one best new method, heavily compared with our method. So it showed that we contribute a good baseline for this community. So the second part of my talk will be talking about the scalability, which is integrating reasoning with learning to accelerate scientific discovery. Scientific discovery in general is a broad topic. Here we are considering a specific topic, which is discovering the physical knowledge from the experimental data. Over the history, it is done by those famous scientists like Isaac Newton, Kepler find the planetary motion, or Avogadro found the ideal gas law. So one of the things that we find is scientist-based discovery is quite slow. It takes their whole life to discover those important laws. And right now, the machine computation is much faster nowadays. So a natural idea is, can we using those fast machine to automate the discovery process, and then it can be useful for us to analyze more and more complex physical phenomena. And the process of using machine to find natural law is called symbolic regression or equation discovery. So here's one of the demonstration where we are having some batch of experimental data, and then we are given some set of allowed operator. And our job is to find a closed form of the equation. So yes, we ask a black box here right now is a symbolic regression method, and then we ask it what is the best symbolic equation. It can be x1 times x2 minus x3 divided by x4. So over the years, there has been a long line of history to advance this domain. Earliest example was proposed by Pat Longley and Herbert Simon. They proposed a method called a series of methods called Bacon. So they wanted to using the algorithm developed at that time to discover the natural law from the data. More recently, genetic programming was proposed as a more sophisticated algorithm to solve this set of problems. Recently, with the recent progress of neural network and large language model, more and more methods like deep reinforcement learning, Monte Carlo tree search, transformer, and large language model are developed to solve this set of problems. However, we find that there's a common limitation in this set of solutions. So they all struggle to solve the equation with a few variables. And when we wanted to analyze those complex phenomena involving a lot of variables, this method will simply just give you a random, no more than random guesses. And the fundamental reason of such a failure is because the space of all the possible equations actually grows exponentially to the input variable. So it becomes more and more challenging if you ask this methodology to process those high-dimensional data. Well, how do we going to attack this problem? Here's one of the running example. So in this running example, we are given a batch of data that we assume we collect from the experiment. The job is to guess the audience an equation that the data, what is the governing equation from this data? So at a first glance, it may be non-trivial for you to directly find the pattern. So how about I simplify the problem a little bit? Well, let me know if you can directly find the solution. Let's take a look at if we're only looking at part of the data. So the data explicitly we are doing here, we control one of the variable x1, take the same value, x1 here equal to -1. And then we find that there's some pattern between x1, x2, x3, and y. That the audience has an answer. I eyeball these few data points. Okay, nice try. So let's verify. X1 times x2, what, minus or plus? Okay, that's a good guess. So it's a -3 and then +4 should be 1. So it seems like this is so one of them could be x1 plus x3 or x1 multiply x2 plus x3. So your answer and this answer, both of them can be considered true. Let's take a look at the other part of the data, which you have x2 take another different value. Here we set it to be 1, x2 equal to 1 for this part of that selected data. So now, does the statement Mutian just proposed still holds? So we can take a look at and verify. So Mutian say that it should be 2.5 times 1 plus 9.5 equal to 12. So actually, Mutian is able to give you a good answer. So in this example, another alternative answer is negative x1 plus x3. So we got we got both of them. So it should be the second one should be x1 plus x3. Sorry. Now we got two guesses. One of them is saying that x1 plus x3. The other of them is -1 plus x3. And promising you they are coming from the same governing, generated from the same governing equation. So the reason that they look different is because we are controlling x2 to take a different value. So it could be x2 because of assignment x2, the sign of those inside before the sub-equation x1 become different. So x2 can be like played here. So it can be some other form of x2. But we know that according to the hypothesis, according to our previous observation, the equation should have this format, something of x1 and plus x3. So actually, the experiment, the interactive experiment with the audience was actually happened from the history. So that here they from the history of Gauss law, the scientists wanted to study this phenomena involving several contributing factors. So they wanted to know the amount of gas, the temperature of the gas, pressure of the gas, and the volume of the gas. So they wanted to know what are the fundamental governing physical law. The first scientist, instead of considering all the variables, he specifically controlled the amount of gas and temperature of the gas to be fixed. He studied only what is the pressure of for the same amount of gas at the same temperature, what is the pressure and what is the volume. He found that pressure times volume equal to a constant. The second scientist, built on top of the previous success, he specifically conduct experiment where set free for the temperature. So he conducts experiment where the pressure, volume, and temperature can take different experimental configuration. So he found that the PV divided by T equal to a constant. The last scientist, Avogadro, he set free for all the process, which is PV divided by NT equal to a constant. The history we just see and then is actually carried out by human being. We call it, the process is called scientific reasoning. And this is saying that we are going to, at the first step, control some set of variable. In the second step, we are going to reduce this set of control variable. Till the last step, we set free for all the controlled variable. So now we have the main design principle of those integrated system. So the input is some experimental data, and then the symbolic regression method is here for you to find the optimal equation. The scientific reasoning module placed here help you to determine what's the hypothesis and what are the controlled and what are the controlled experimental how to do the controlled experiments. And then finally, we will give you the best fitted equation. Here is a analogy of the previous principle. So we wanted to find the equation involving 4 variables. And then instead of directly get some data and then ask a symbolic regression method to find the best equation, we wanted to build the equation from simple to complex, following our scientific reasoning principle. And here we have an extra assumption, meaning that we have those data oracle that can return those control variable experiments. At the first step, we are specifically considering controlling the variable 2, 3, 4. So here you will find that x2 in this data batch equal to 0.5, and then x3 equal to 0.1, and x4 equal to 0.7. Only x1 take different value. So under this setting, it seems all the 2, 3, 4 behave like a constant. And then only x1, the relationship of x1 and y will be discovered. So we ask a classic symbolic regression method, and then it will give us, based on this data, the best expression tree. So this expression tree describes the equation of x1 times some constant minus another constant. The constant here behave like a constant could be we are deliberately controlling those rest variables. So we will find it out in the future iteration. Or all those constants are real constants that will not change if you release those controlled variables. So in the second round, we have a refined hypothesis. Basically, the equation should look like this format. It should be some x1 multiply some sub-expression and minus some other sub-expression. And we are set free for the variable x2. So we only control x3 and x4. Now the job is to find the governing equation of x1 and x2 and y. So we ask a class symbolic regression to do the job, and it will help us to find out that the first part is still a sub-expression of constant coefficient. The second one is actually a sub-expression of variable x2. So now we have refined our hypothesis by removing one of the controlled variable. Let's continue this row. Here we have another hypothesis that say that the equation should have some structure, that it should be x1 times some sub-expression minus x2 times some other sub-expression. And we are only controlling the variable x4 here. The task is to find the governing equation for x1, x2, and x3. We ask symbolic regression to do this method, and we find that the hypothesis is refined to be one of the sub-expression is x3, and then the other is still a constant. Finally, we set free for all the variable, and then we have a more refined hypothesis. The structure of those equations should like this format. And then we ask a symbolic regression to do the method to improve the prediction, and you find that the constant can be replaced with a sub-expression, which is exactly x4 here. So throughout this process, we find that we do not rely on a specific symbolic regression method. It can be genetic programming or reinforcement learning, Monte Carlo research, or to the latest large language model. And here's we wanted to understand why our method can help you to accelerate the search. So here's a statement which we say that scientific reasoning brings an exponential reduction of the search space for a class of equation. Here, the class of equation we consider here explicitly look like this format. So it should be x1. It can be x1 plus x2 times another x3 plus x4 till the end. So we find if for a classic symbolic regression method that you're starting from exploring the whole search space, the space including all the possible equations, it would the size could be exponential to the number of variables here. And then if you follow the scientific reasoning that you follow from a small only an equation involving a few variables to all the variables, then it can reduce the whole space from the exponential to the polynomial size. We evaluated our method with a line of recent proposed methodology on a data set involving 10, 20, up to 50 variables. Here, the number is evaluated on the normalized mean square error, meaning that we got a governing equation give you the input, and then we got some best predicted equation predicted by any of the method. So we evaluate whether the ground truth output or the evaluated output by our predicted equation, they are the same. So if the error is large, meaning that the prediction is incorrect. If the error is very small, meaning that we got an almost correct prediction. So from this method, from this table, we find that our method can help you to scale up to data set involving high dimensional data. So we evaluated on up to 50 variables. So this can help us to bridge the recent methodology to the complex experimental studies that needed in our real study, in our real world. Here's a real-world application of our developed symbolic regression method. So the video we see here is from material science. They give us some video, ask to keep track of those bubbles. The bubble in the video is called tiny cavity in copper. So the bubble will move around if you look at the annotated figure, and then the bubble size will shrink or become larger. So previously, this all done by their domain scientists. They needed to human annotate those data and then keep track of those bubbles. So here, what we do is, given those video, we use some computer vision algorithm to track those bubbles, and then we're using our developed software to find the governing PDE, and then the task is to learn the material science, theoretical material scientist told us the structure of the PDE, and our job is to learn the coefficient, the best coefficient from the annotated data. We find that using this developed pipeline of symbolic regression, it helps us to scientific discovery on those nanavoid size, which means that over a long period, those bubble size is consistently shrinking. This was not obvious according to their previous history, which means they only are able to analyze for a short period of video that this consistent size shrinking was not obvious for them at that time. So using those automated AI-driven tools can help to advance the research that at the intersection of material science and AI. So the main takeaway for my research is we try to propose a new formulation by integrating machine learning model with automated reasoning solver. The benefits of this integration is we have formal guarantee on constraint satisfaction, and then we have scalability property allow us to learn on higher dimensional data with improved accuracy. Now, the final conclusion, the final part is about the future work, what I'm planning to do in the future. So the first research thrust is to embed reasoning in learning to accelerate scientific discovery. Actually, in the scientific world, there are more and more problems that can be considered. For example, here are some problems on spin nodal decomposition, which you can think of it there, a mix of oil and water. The oil will combine with each other over time. The other one is called dendritic solidification. You can one of the representative example is the growth of snowflake. These problems are and also their family are widely existing material scientists. The task of it is to ask what is the governing dynamics of physical law in those phenomena. So I can continue this role to propose advanced reasoning algorithm to accelerate the discovery of such scientific problem. The second one is formal reasoning for large language model. Basically, we wanted to combine the informal language-based description with some formal reasoning mechanism like symbolic proof or rule-based derivation for a class of verifiable and accurate prediction tasks. The task can be how can we solve those hard mathematical problems when we have access to large language model and the symbolic solver. For example, a group of researchers are considering those geometry problems. And this does not limit it to 2D geometry. We can extend it to 3D geometry, which was not there. Right now, we can extend the scope of this mathematical problem. And also, some of researchers consider more advanced mathematical problem. They call it serial proving problem. This also requires a symbolic solver to verify the correctness of the proof, and also large language model to give you a prediction what is the useful proof, what is a useful theorem for you to prove a challenging problem. And the other task is to, they call it AI for code. And basically, you give some description of the problem that you wanted to do. And then you want an integrated system that can give you an executable code. The code should be correct and executable. So this including that the system can do competitive programming in real time. Also, it can be like you want the system to generate some efficient low-level execution. Can be this was currently some topic discussed like ML system. So they wanted to using human being to design some low-level efficient code. We can using the this formal reasoning system to help to suggest some possible better implementation that was never thought about by human engineer. And also some application could be program repair that you wanted to repair a buggy code so that you can fix the code and then make sure that it's executable and also make sure it is correct. And also some test function generation depends on the context of data set. So these are the possible topics that I would like to pursue in the future, which all belong to the family of formal reasoning or large language model. This is basically the whole topic of my thesis defense, and thank you for listening.
Okay, so first, do we have questions from the audience?